Okay? In this particular example, mathematical induction is under Bernolli'S inequality. So Bernolli'S inequality is telling us that we can prove some statements in mathematical induction that contains inequality sign. Okay, a good place to do is to consider the statement to be P of n, which is 3 raised to the power n is bigger or equal to 2n plus 1. Okay, at n equal to 1, so what we'll be having is 3 raised to the power 1 greater than or equal to 2n plus 1 by replacing n with 1 in this statement. So what we'll be having is 3 is greater than or equal to 2 plus 1 is 3. 3 is not greater than 3, but 3 is equal to 3, so the statement is true. We have that P of 1 is true. So if P of 1 is true, we assume that P of k is true for some k greater than or equal to 1. So if k is greater than or equal to 1, anywhere we see n here, we replace it with k. So we have here to be 3 raised to the power k is greater than or equal to 2k plus 1. Okay? So that is the assumption state. We now check if P of k plus 1 is also true. Is also true for some k element of natural number. Okay? So when we want to study this, anywhere we see n in this practice problem, we put k plus 1 to be having here to be 3 raised to the power k plus 1 is greater than or equal to 2k plus 1. Then plus 1. By replacing the value of n here with k plus 1, this is what we have. Okay? Since we have this, we can check whether the left hand side is greater than or equal to the right hand side. So we can check whether the right hand side is less than or equal to the left hand side. Let's start from the left hand side. Okay, let me write out the question here so that you understand it well. K plus 1 is greater than or equal to 2k plus 1 plus 1. Okay? So let's pick the left hand side. 3 raised to the power k plus 1. We have, according to indices, that this statement is 3 raised to the power 1 into the bracket of 3 raised to the power k. Okay? As this may have it, we have the corresponding value of 3 raised to the power k in the assumption as 3 raised to the power k is greater than 2k plus 1. So if we put greater than or equal to sign, we can change 3 raised to the power k here to 2k plus 1 to have 3 into the bracket of, instead of writing 3 raised to the power k because we have implied triangular inequality, we'll change it to 2k plus 1. Okay, we can open the bracket to have that this corresponds to 3 times 2k is 6k, 3 times 1 is 3. Okay? This is the left hand side. Left hand side, where we started. We started with left hand side. So this left hand side, our aim is to prove that this left hand side is greater than the right hand side. So if you look at this value now, is it not greater than this value? It is greater. You say that it is greater than or equal to the right hand side, which is 2k plus 3. This is the right hand side and this is the left hand side. The left hand side is 6k plus 3, but the right hand side is 2k plus 3. Let's check whether this is the actual value of the right hand side, which we have here to be 2k plus 2 plus 1. So 2 is common, we'll factor 2 out. We have 2 into the bracket of k plus 1 plus 1, which is the same thing as the right hand side. And that is proved. Okay, so since P of k plus 1 is also true, this implies that P of k plus 1 is also true. Hence, P of n is true for all n elements of natural number. Okay, in this type of Bernolli'S inequality in mathematical induction, we have to consider as n equal to 1 to check P of 1 if it's true. So we have in here to be 1 plus p raised to the power 1 is greater than or equal to 1 plus 1 multiplied by p. Okay, so finally we'll be having 1 plus p is greater than or equal to 1 plus p. 1 plus p is not greater than 1 plus p, but it's equal to 1 plus p. So P of 1 statement is true. So the second step is to assume that P of k is true for some k greater than or equal to 1. Okay, so what it means is anywhere we see n in this practice problem, we call it k. So what we'll be having here is 1 plus p raised to the power k is greater than or equal to 1 plus kp. Okay, this is the assumption state. Now we will check in the third step, check if p of k plus 1 is also true. Also true for some k elements of natural number. So what it means is anywhere we see n in this practice problem, we replace it with k plus 1. So what we'll be having is 1 plus p raised to the power k plus 1 is greater than or equal to 1 plus k plus 1 all multiplied by p. Okay, so we're going to start from the left hand side to prove the right hand side and see what we have there. So if we have this, the left hand side is 1 plus p raised to the power k plus 1. Let's check if it is greater than or equal to the right hand side. So what we have in here is to express it using indices. Here is the same thing as 1 plus p raised to the power 1 multiplied by 1 plus p raised to the power k. Okay, so in the assumption we have that 1 plus p raised to the power k is greater than or equal to. So using this inequality property, we change this left hand side to this to this value. So 1 plus p raised to the power k is the same thing as 1 plus p raised to the power k is the same thing as 1 plus kp by assumption. Okay, so we multiply out. 1 times 1 will give me 1. 1 times kp will give me kp. P times 1 will give me p. And p times kp will give me kp squared. Okay, we started with linear when the highest power of p or x is or n is 1. So you see we have a problem here, which is quadratic p, which is very wrong. We have to eliminate it using inequality sign by changing that young man there to be 1 plus kp plus p. This is null in the solution because we are trying to prove that this left hand side is greater than or equal to the right hand side. Okay, so this statement here is the left hand side, and we know that this thing is bigger than the right hand side. This particular statement here, that is the reason why we have to change the whole thing in the left hand side and say that it is greater than the right hand side. Okay, so p is common, we factor it out. We have 1 plus k plus 1 all multiplied by p, which is the same thing with what we have in our right hand side. So what we say is p of k plus 1 is also true. Hence p of n is true for all n elements of natural number. So note the trick. If after expanding the left hand side and you discover that the statement you have here is bigger than what you have in the right hand side according to the statement, you can say it is greater than or equal to with that inequality that is there and replace it with the right hand side and make sure it corresponds with the exact value in the right hand side as we did in the previous video.